So we've looked at the two main vector operations of addition and scaling by a number. And those are all the things we really need to be able to do to define what we mean by a vector, the mathematical properties that a vector has. Now we can move on to define two things: the length of a vector, also called its size, and the dot product of a vector, also called its inner scalar or projection product. The dot product is this huge and amazing concept in linear algebra with huge numbers of implications, and we'll only be able to touch on a few parts here, but enjoy, it's one of the most beautiful parts of linear algebra. So when we defined a vector initially, say this guy R here, we did it without reference to any coordinate system. In fact, as a geometric object, this thing R just has two properties: its length and its direction, that it's pointing that way. So irrespective of the coordinate system we decided to use, we want to know how to calculate these two properties of length and direction. If the coordinate system was constructed out of two unit vectors that were orthogonal to each other, like I here and J here in 2D, then we can say that R is equal to A times I plus B times J. And when I say unit about I and J, I mean they're of length 1, which people will often denote by putting a little hat over them like this. Then from Pythagoras, we can say that the length of R is given by the hypotenuse. So what I mean by that is, if we draw a little triangle here, then we've got this length here is AI's. And so if we write the length being, well, with these two little vertical lines, it's just of length A, because I is of length 1, right? And this side here is BJ's, and that's of length B. So this side here is, from Pythagoras, is just A squared plus B squared, all square rooted, and that's the size of R. So we can write down R, quite often people will do this, write R down like this, just ignoring the I and J and writing it as a column vector. So R is equal to AB. And the size of R, we write down as being the square root of A squared plus B squared. Now we've done this for two spatial directions defined by unit vectors I and J that are at right angles to each other. But this definition of the size of a vector is more general than that. It doesn't matter if the different components of the vector are dimensions in space, like here, or even things of different physical units like length and time and price. We still define the size of a vector through the sums of the squares of its components. The next thing we're going to do is to define the dot product, one way among several of multiplying, if you like, two vectors together. If we have two vectors R and S here, R here has components Ri, Rj, so R in the I direction, R in the J direction, and S has components Si and Sj. Then we define R dotted with S to be given by multiplying the I components together, so that's Ri times Si, and adding the J components together, so that's Rj times Sj. That is, the dot product is just a number, a scalar number, like 3, given by multiplying the components of the vector together in turn and adding those up. So in this case, that would be 3 and 2 for the Rij, and minus 1 and 2 for S. So if we do that, then we get a sum that R dot S is equal to minus 3 plus 4, which gives us 1. So R dot S, in this case, is just 1. Now, we need to prove some properties of the dot product. First, it's commutative. So, commutative. And what commutative means is that R dot S is equal to S dot R. It doesn't matter which way round we do it. And it doesn't matter because when we put these numbers in here, if we interchange those, the R's and S's, we get the same thing when we multiply minus 1 by 3. It's the same as 3 times minus 1. So it doesn't matter which way round we do the dot product. S dot R is equal to R dot S. which means it's commutative. The second property we want to prove is that the dot product is distributive over addition, by which I mean that if I've got a third vector here now, t, that r dotted with s plus t is equal to r dotted with s plus r dotted with t. I can multiply it out in that kind of way. This probably feels kind of mundane or obvious, but let's prove it in the general case. So let's say I've got some n-dimensional vector r, components r1, r2, all the way up to rn. And s is the same, has components s1, s2, all the way up to sn. And t has components t1, t2, all the way up to tn. Then let's multiply it out. So if we take the left-hand side, r dotted with s plus t, that's going to be equal to r1 times s1 plus t1, if we take the components. And then r2, component r2, times components s2 plus t2. And then all the dimensions in between. And then finally rn times sn plus tn. And then what we can do is we can then separate that out. So we've got, multiply that out. So we've got r1 s1 plus r1 t1 plus r2 s2 plus r2 t2 plus all the ones in between rn sn plus rn tn. And then we can collect them together because we've got the r1 s1 terms, r2 s2 all the way to rn sn, and that's of course just equal to r dotted with s. And if we collect the rt terms together, we've got r1 t1, r2 t2, all the ones in between, and rn tn, and that's just r dotted with t. So we've demonstrated that this is in fact true, that you can pull out plus signs and dots in this way, which is called being distributive over addition. The third thing we want to look at is what's called associativity. So that is, if we take a vector, a dot product, and we've got r dotted with some multiple of s, where a is just a number, it's just a scalar number. So we're multiplying s by a scalar, and what we're going to say is that that is equal to a times r dotted with s. And that means that it's associative over scalar multiplication. And we can prove that quite easily just in the 2D case. So if we say we've got r1 times a s1 plus r2 times a s2, that's the left-hand side just for a two-dimensional vector. Then we can pull the a out, right? So we can take the a out of both of these. And so then we've got r1 s1 plus r2 s2. And that's just r dot s, a times r dot s. So this is in fact true. And so we've got our three properties that the dot product is commutative, we can interchange it. It's distributive over addition, which is this expression. And it's associative over scalar multiplication. We can just pull out scalar numbers out. As an aside, sometimes you'll see people in physics and engineering write vectors in bold and numbers or scalars in normal font. Or they'll underline their vectors to easily distinguish them from things that are just scalars. Whereas in maths and computer science, people don't tend to do that. It's just a notation difference between different communities, and it's not anything fundamental to worry about. The last thing we need to do before we can move on is draw out the link between the dot product and the length or modulus of a vector. If I take a vector and dot it with itself, so r dotted with r, what I get is just the sums of the squares of its components. So I get, r1 times r1 plus r2 times r2, and all the others if there are all the others. So I get r1 squared plus r2 squared. Now that's quite interesting because that means if I take the dot product of a vector with itself, I get the square of its size, of its modulus. So that is, that equals r1 plus r2 squared square rooted, all squared. So that's mod r squared. So if we want to get the size of a vector, we can do that just by dotting the vector with itself and taking the square root. And that's really kind of neat and really, hopefully, quite satisfying.